Very good morning to all of you. We'll start here the third session of this workshop. I really thanks to Dr. Kolle sir who is on this portal today. I'm very happy. Anyway, so let me just brief out. In the first sessions, we have discussed about protection, deprotection, which is the need of retrosynthesis. In the second session, that is the second day of the workshop, we have discussed about the basics of retrosynthesis. And in the third sessions, we are going to see the strategies and exact application, how to tackle the big molecules with the help of this great technique of designing of the organic molecules. So let me just brief you today what we're going to discuss. That in the first half, we're going to discuss about some of the strategies to be applied for the retrosynthesis, and in the next half, that is the last sessions, will be completely application based. So let me start with the today's session. So let's see the general strategies in designing of the organic molecules. What precautions you need to do or you need to take. In fact, while doing the cleavage or disconnections, if you have big molecules, you should not disconnect anywhere. So you have to think logically the portion of the molecules which is exactly middle point. Suppose if you are getting a exact two half of the molecules, you can apply the convergent synthesis type of things as well if you are getting the exact two half, and that is very easy and cost effective way as well as in terms of the yield. That if this is the molecules I have shown you here, if this molecule, if you are disconnect over here, if you are disconnect over here or here, it is not point to have quick access to the whole molecules, because it's a fragment and it is not so easy to go with the reactions which is reliable, particularly carbon-carbon bond formations. Whereas if there is a possibility of nucleophilic substitution or nucleophilic addition type of reactions are possible, the reliability of such type of reactions are very high. So we have to always think wherever there is a functional group like OH or electron-rich group like carbonyl group, or it may be the OH or NH2, there you have to think about the cleavage. So this is the general strategy, that you can cleave these molecules over here perfectly or here. So then you can easily get the access or proper disconnections to get the total synthesis of these molecules. Now, if we disconnect over here, what fragments you are going to get here? That this is going to be a synthon having a positive charge over here and the negative charge over here. All right. So these are the synthons. But in fact, we have in the literature, if this is the synthons, it will resemble to the carbonyl group. That is what aldehyde. And this is the nucleophile, which should be the organometallics part. So this is your RMGX organometallics. And this is just one-step reactions. When you treat this GR with this propanol, you can get the quick access to this molecule. Whereas, if suppose you thought, I will disconnect over here. Okay, suppose you thought that you will disconnect over here, what synthons you will get probably? You will get plus minus charges like this, or it may be probably this will be plus and minus. Now the point to join this back, it is very tough. That carbon-carbon bond formations where there is no any sort of clue, so it is very tough. So if you cleave it here, you have to think twice what reactions I will use for the getting back the molecules. So while doing such types of disconnections, it is not useful. So you have to use some the cleverness in the disconnections. That is what the strategy which is proposed by the Woodward's. So that is particularly the book which where I have taken these particular references. Anyway, more to the next. This is what the exact synthesis of these molecules, that if this GR is not available, you can synthesize from halide, you treat it with the magnesium metal, you will get the in situ formation of this Grignard region, and then you will treat it with the propanol and you will get the target molecule. This is what the actual synthesis. Now, this is the another molecule where you also you have to think about the cleavage of while doing the cleavage, you have to find that okay, where I will disconnect over here or somewhere here. So if I do disconnect around this area of these molecules, this is the anisole type of derivative which is available in the market. If I suppose think about this is N-methylation of the piperidine type of thing, which is also available in the market. So need not to think that way. So you just think about the where is the proper that fragment, two big fragments of these molecules you will get, and that is the correct way to have a disconnection over here. So if I disconnect over here, I will get here some sort of your uh, symptoms like over here positive charge and this is negative charge. So this negative charge will be the part of your Grignard reagent. So this is what Grignard, and then it will be your carbonyl group. So this is your 4-oxo piperidine type of derivative you will get. And it is very easy to have the access to these target molecules. Now, while doing this synthesis, you can think about further that how to get this, and this is very simple now, that N-methylation of this nitrogen, it is possible. Now, these are the similar type of examples over here, very similar, that you have to find out where to cleave these molecules for the synthesis. You can disconnect over here or you can disconnect over here. It is acceptable, but moreover, you will find the disconnection over here. The reason behind the acetylenic that particular GR will be added very comfortably across the acetophenone and you will get the quick access. Whereas if you disconnect over here, then you have to think about to get this particularly that acetyl methyl ketone, how to synthesize. So this is the clever way to cleave the molecules. So this is the correct way that you can disconnect over here. Here also you can disconnect over here. Ethyl magnesium bromide will be the your reagent across the acetophenone, and this is will give the quick access. Whereas in these molecules, if you disconnect over here, this cyclohexyl magnesium bromide will be the GR, that is the Grignard reagent organometallic compound, which is easily available in the market. And this remaining will be the acetone. So acetone, when react with the Grignard reagent, you will get the quick access to this tertiary alcohol. Whereas this is the another molecules where you have to be very logical that if I disconnect over here, this will be the part of GR and this will be the benzophenone, and which is easily available in the market. So this way you have to be logical while doing the disconnections. The second strategy, that if you have very big molecules, some point you may have like a keratin type of molecules, or this is a very huge molecule you can see over here. Such types of molecules need not to like cleave one branch by branch. You have to think logically. If there are these similarity in the molecules, the fragment, if the two fragments are exactly similar, then the symmetry of that molecule must be there. So symmetry means that reaction will work twice. The reagents will be adding twice and you will getting the two branches of that particular molecules. Now suppose take this example of tertiary alcohol. If I do the disconnection over here as well as here simultaneously, that this part and this part is symmetrical. So I do understand that if I do disconnect, double disconnection, that is we call carbon-carbon double disconnections, then I will end up with this. This should be your ester and this should be your Grignard reagent. So Grignard reagent, you will get it from any source. Okay. So that is very easy to synthesize for the part of that molecules, how big it is. Okay. But question is what here, that if you came across the very big molecules and the two branches of that molecules look similar, then you have to think about that there must be a symmetry. So this is what the symmetry where we have did the double disconnections. I will end up with this will be the ester. Normally when we do the double disconnections of the tertiary alcohols, normally that double disconnections normally will leads to the double addition of Grignard reagents across the esters. You know the organometallic reactions. When organometallic, that is particularly Grignard reagents, when reacts with ester, there is a double alkyl group addition. That is what nucleophilic addition of the grignard reagent will be twice, because the intermediate will form a ketone and ketone further react with the grignard reagent, and you get the final product. That is what we call as a tertiary alcohol. So you have to think in a logical way. Whenever you got the symmetry, and that symmetry is with the tertiary alcohol, then you have to logically think that reactions will be the double GR with the acetone, sorry, with the ester, because ester will give the double addition of the grignard reagents and end up with the final product, that is tertiary alcohol. Okay, so if you are getting a secondary alcohol, then you have to think about it. Maybe you are sort of maybe the aldehyde sort of thing. If you are getting primary, then you should have a formaldehyde sort of carbonyl group. So that way, you have to keep the logics in your mind, that whenever you are doing the cleavage, and if you are having the target primary alcohol or secondary alcohol or the tertiary alcohol, so logically you have to think this way. So this is very simple strategic in this way of strategy, that we have double disconnect, and we will have the starting material as a ester and the grignard reagent. Now suppose we have a question that this GR is not easy to synthesize. So what to do now? We can go one by one step ahead. That how to get this? This must be the part of your alkyl halide. So the alkyl halide can be converted into alcohol. Suppose this is your alcohol. Now this alcohol can be synthesized further by doing the disconnection over here. If I do the disconnection over here, this will be a nucleophile and this will be your electrophilic. And if this is electrophilic symptom, this will be the epoxide and this will be the grignard reagent. So this isopropyl magnesium bromide, when react with the epoxide, it will open like this and you will have this alcohol. When this alcohol treated with PBr3, there is a nucleophilic substitution, that OH will be substituted with the Br and you will have halide. And that halide, when treated with the Mg, you will get the target molecule, which is your grignard reagent only. And that grignard reagent, two molecules, when reacts with the particularly ester, you will get the target molecule, which is shown here in the synthesis. This is your starting material, react with epoxide. First it is converted to the GR, and then epoxide, you will get alcohol treated with PBr3, and you will have here halide. And this halide will further react with Mg and treated with the ester to get your target molecule. This is what the very logical way of synthesis, while if the molecule is very big and having a symmetry. Now this is the molecules where you can easily work out that this 2 pH and this 2 pH, that means there is a symmetry. What symmetry it must be? This is the ether. Normally how the ether will form in case of the Current type of ring, there is a condensation of diol normally. So that if we do the reverse of that, that is what retro, we do the hydrolyze sort of thing, H and OH over here, we'll get here diol. Now, if you see this molecule, you will find here the symmetry, exact symmetry. That means you need to think about logically some double grignard reagents or two types of reagents will be added. So if you think about this particular A, this is your tertiary alcohol as well. This is your tertiary alcohol. As I told you, when the two fragments of the tertiary alcohols are same, then think about the grignard reagent will be added across the ester. So this will be two molecules of the like ester group. So nothing but this is the ethyl your succinate. Now this diethyl succinate, when reacts with the 4 moles of PHMgBr, that is phenyl magnesium bromide, you will end up with the target molecules. So this is very interesting, and this is very we can say that there are great advantages over here while doing the synthesis of such types of things. If you think in a normal way, okay, I will break this one and then this one and then this one, so it will be very tough to get into the target molecules. So you have to think in a the strategies which is proposed by the applications of the particular retrosynthesis. Move on to the next. Look at here. This is a huge molecules. When we look at these molecules, we do scared. Oh, how to synthesize such a big molecules? But if we think logically, by knowing the concepts of retrosynthesis, that symmetry may be the point of synthesis, then we can easily work out, okay, this fragment and this fragment looks very bit similar. So this may be the part of your, because there is olefin, and this is again olefin. So this may be the part of olefin. That means Wittig reaction might be the use over here. So this portion and this portion is the part of Wittig reaction. Now further, if you see this molecules or this molecule here, you can disconnect over here also. So this fragment and this fragment looks a bit similar. So this way, whenever you come across with the huge molecules, there must be some sort of symmetry. So you have to think logically. This is just to show you the scary example and how to make it very simple. Now, another important aspects you have to consider in retrosynthesis is the high yielding steps. That in the process of reactions, particularly that is synthesis, you should always prefer to give the preference particularly to the high yielding steps. Instead, the reactions which are very sensitive for the side chain reaction or byproduct formation, that reactions normally you have to avoid. Now here, take the example over here. We will explain with the example. So this is your alcohol. This alcohol, when we target it by two way. So the first way I will show you by this A. So when I disconnect over here, I will have this is a positive charge, this is negative charge synthones, and this will be the formaldehyde, and this is your phenyl magnesium, benzyl magnesium bromide, that is your GR. When we do these reactions, uh, now formaldehyde is a so sensitive reactive starting material. When this formaldehyde reacts with aromatic ring, instead of going towards the Grignard reagent some point, it may go towards the some sort of alkylations sort of thing. Okay, so your target was to get your alcohol, but you are getting some side product, and that will not be uh, tolerated in case of the getting the synthesis of the big molecules or important molecules of your choice or of your research point of view. If you are targeting very important the target molecules, and if you're getting a side chain reactions, so you will lose your precious starting material. So you have to avoid such type of reactions which are not good yielding, as well as showing the side chain reactions or the byproduct formation quantitative. Whereas there are the different ways, as I already mentioned in the earlier talk, that retrosynthesis is such a platform where there is no any single route, that if you want to go to one place, there is a one particular highway to go there. But here there are multiple ways. The target or the destination is with the networks of the roads. You can choose any one, but you have to find out which one is the best and safe for your journey. So here also in retrosynthesis, you have multiple ways to synthesize these target molecules, but which one is better, you have to select by knowing the knowledge of the chemistry, by knowing the knowledge of the reactions which you come across. So this sort of hydroxymethylation reaction is the side chain reactions which will normally uh, avoid the target molecule synthesis. So instead, if you go to the B route, disconnect over here, you will have epoxide and phenyl magnesium bromide as a starting material, and this reaction works very clean because this phenyl magnesium will attack very comfortably and you will get the target molecule. So you would always look into the high yielding steps. Now, number of times we just waste our energy on synthesizing the material which is easily available in the market. Okay, suppose look at here, this is the molecules you are targeting. Now this is the molecule, looks very huge, but there is a symmetry. So this point and this point having a symmetry. Now if I disconnect over here, as I told you, this may be the part of your Grignard reagent. So the twice this Grignard reagent added. Across what? This acrylate. Now this acrylate, now if you are not having a knowledge that this acrylate may be available in the market in a very cheap uh, cost, it's not so expensive, but instead you are putting the energy to synthesize this. How you will you apply your logic? Oh no, there is a double bond, I can synthesize this double bond. How this double bond can be synthesized? Okay, this may be your carbonyl group, and this is your ester group over here, like this, and this may be the Wittig reagent. What Wittig reagent you will get? H3 P double bond H2. So this one. Okay, and this reacts with this and you will get this back. So you will logically think this, I'm sure, whenever you are not having the knowledge that this starting material is very cheap, cheaply available in the market. Why to waste our energy on synthesizing this? Now, if you are targeting this reaction, this is not so easy. You know, this having a Wittig reagent with the methyl bromide, triphenyl phosphine, you have to do this one step, then followed by the another steps. And as I told you in the earlier talk, that the type of synthesis, that linear or it may be the convergent synthesis, if the steps are increasing, okay, then what will happen? Your target molecule yield will tremendously goes down. So you have to think logically that steps of the synthesis should be minimum to get the maximum yield. So unnecessary, you should not go with this synthesizing the molecule which is cheaply available in the market. So there are many such molecules. There is a literature library that is a we call as a catalogs available. Sigma Aldrich, or there is many vendors in the market. They sell the chemicals, and you will find that this sort of moieties particularly, you see this one, all this, they are easily available and in a cheap cost, all this particularly. So need not to synthesize at all. They are available with the cheap cost. So you can select this and directly you can start your synthesis. So this is what the important point of the retrosynthesis, that you have to think in a logical way, that need not to put your energy to synthesize all the fragments. Now look at here. This is the one synthesis where you can easily work out how the chiefly available starting material you can select. Now this is the molecules where you can have the tertiary alcohol in hand. If you disconnect over here, okay, then you will have the B root particularly, you will have here this halide, particularly halide in the sense Grignard reagent, and this is your acetophenone type of compound. Now if I disconnect over A, then I will have here, this is your dicarbonyl compound and the your bromobenzene type of thing. Now to get the access to this acetophenone type of things, I can easily get it from the toluene on acylations. I will end up with this. And then this acetophenone type of thing, okay, can be react with the Grignard reagents which will be synthesized. So how that this particular molecule or this particular molecule is synthesized, this can be further synthesized by because it is not possible directly to have the Mg2 react over here, because there are limitations of Grignard reagent that their carbonyl group should not be there. So it should be protected and then react with the Mg. So we did here, this is your starting material now, acrolein. Okay, so acrolein when react protected and treated with Mg will get the Grignard reagent, and treated with acetophenone you will get the target molecule. So this way you can do the synthesis of such a big molecule. Now the next point in the synthesis is that we are going to target it now each functional group, including alcohol, it may be the carbonyl, aldehyde, ketones, amines, amide. Okay, and we are doing here the carbon-carbon disconnection. Some of the things already we have had a little discussions in the first talk. That was the just what we have said, general discussion about the one group, 1, 2, 1, 3 difunctionalized compound. Now here we are going to repeat the a little bit same thing, but in a detail, that carbon-carbon disconnections with uh, the one group. That means in the molecule there is a one functional group which will involve and which will some part facilitate the process of disconnections. So we have targeted here first the alcohol. Now this alcohol, with including stereochemistry also we are going to talk. Suppose we have a primary alcohol. Now in general, if you have primary, secondary, tertiary, there are fixed route. Most of the cases, the organometallic chemistry is mostly exploited while synthesizing the primary, secondary, and tertiary alcohols. So let's have an example to synthesize this primary alcohol. How we'll cleave it here? We'll do the disconnection over here. This is the part of Grignard reagent that can be easily synthesized from this halide and formal here. Suppose as we look into the target molecules and we saw there is a primary alcohol. So think logically, there must be a reactions with Grignard reagents with the formaldehyde. So this is one clue in the retrosynthesis particularly I must mention over here. So this halide, the chemistry is as usual now. You will give you the Grignard, react with the formaldehyde, you will get the primary alcohol. Suppose if you want a secondary, then you can change that to the uh, aldehydic steps. So I have an example. So if this is the secondary alcohol, you disconnect in a two-way. If I disconnect B way, so what I will get? I will get here aldehyde and I will get here Grignard reagent. If I do the A way, so A way also give you the what? This is your aldehyde and this is your Grignard reagent. Both ways possible. Okay. And this particularly when react with this and this reacts with this, you will get the target molecule which is same. So both the ways are same. Both the ways are same. It is not said anywhere that you will follow the A or you will follow the B. But you have to think logically that whether you have PHMGBr available in the market or in the lab, or whether you have this particular Grignard reagent available with you. So this will choose you the path to where to disconnect. So this is what the availability of the chemicals with the laboratory which you where you're working. But at present, this is for the research student. But at present, as a student of MSc, we don't bother about that availability. We bother about what we should get the knowledge how to disconnect and how to join back. So for research point of view, you have to think logically that whether it is available or not, then and then you can have A route or B route. Next, if you have tertiary alcohol, again, tertiary alcohol, as I told you, if I disconnect over here, the first part will be the Grignard reagent and second will be the ketone. And this ketone, it varies on the substitution pattern. It may be the acetone, acetophenone, and so on. So this, when react with this, you will get the acetophenone derivative, that is the tertiary alcohol. Okay, so it's very simple. Now let's have a couple of examples based on this primary, secondary, and tertiary. Suppose we have here this tertiary alcohol. How to target this? No doubt, we'll disconnect over here. This will be minus, this will be plus, and this plus will be the acetone, and this will be the Grignard reagent. And this Grignard reagent, if it is not available, we can go back one step, and this will be the halide. And this halide, when react with Mg in the dry condition of ether, you will get the Grignard reagent in situ. In situ ka matlab kya ho raha hai? In the flask, you have taken the halide and added magnesium metal in a dry condition, completely dry condition. Your solvent should be completely dried and it should be dried over the sodium metal. And then completely anhydrous conditions, you have to pour the acetone and then the reactions will be there. So this is what the in situ is. So you need not to prepare it and then you have to externally you have to add. In the same flask, you can add the acetone, that is we call as a in situ preparation, or there are some of the Grignard reagent available in the bottle grade. So you have to again use a very dry conditions for these reactions because it is so sensitive reagent. Moisture can quench that particular reagent. Now let's have this example. If you have this alcohol, if I disconnect over here, I will have this ketone and this GR, and you can easily get the access to this target molecules. This is another secondary alcohol. If I disconnect over here, now we are talking about carbon-carbon disconnections. Okay, and that to what? The one group disconnection. That one group is involved in the process of synthesis. That is what alcohol. If I disconnect over here, what I will get here? This positive charge here and negative charge here. Negative will be the part of Grignard reagent, that is nucleophilic, and this will be your carbonyl group, that is a cyclopentyl aldehyde. And this cyclopentyl aldehyde, when reacts with, okay, if you want to synthesize this cyclopentyl aldehyde also, you can do it. Do the FGI, and that FGI will be the alcohol, that is primary alcohol. And disconnect over here and take this cyclopentyl magnesium bromide as a Grignard reagent and treat it with formaldehyde for the synthesis of primary alcohol. So that's, we have started with the bromocyclopentane. When react with the magnesium metal, in situ there is a formation of GR and which will be treated with the formaldehyde. We will get the primary alcohol, do the oxidations, control oxidation, that is PCC. This is we call as a PCC. pyridium chlorochromate, that is a Corey's reagent. Okay, Corey's reagent, what it will do? It will do the control oxidation that to the aldehydic steps. And to this aldehyde, when this GR will treat it, you will end up with the target molecule, which is in excellent yield. Okay, so this is how the synthesis will be achieved. Now, suppose we have here these molecules. This is again tertiary alcohol. Now, look at here, this tertiary alcohol. If you target it to disconnect over here, what you will have a ketone. That means this is a positive charge and this will be the negative charge. So this negative synthons. Now this particular negative synthons will be possible to have vinyl magnesium bromide. That is the available reagent. You can directly start with your reaction with vinyl magnesium bromide. That is CH2, CH2CH and MgBr. That is GR. Okay, it is very tough to write here. All right, so this is GR particularly. You can just add MgBr over here. That is what the meaning. So this is available in the market. And you can do the one-step reaction. This vinyl magnesium bromide, when they react with the ketone, you will get this. But as already I have discussed with you, the handling with the Grignard reagent is so sensitive. And in the laboratory you are working with, there is no such facilities to have the such a desiccating environment that is free from moisture, and you don't have that assembly. So simple reagents are available, and that simple reagent can be used by using the acetylene gas. So this acetylene is so reactive. If you treat it with any base, mild base, maybe sodamide, it will generate the nucleophile, because this is having acidic proton, because of the carbon is highly electronegative because of the sp hybridizations, and this will give straight away addition across the acetone straight away. So this is in situ reaction. Simply what you're going to do, take acetone, add sodium metal in liquid ammonia and pass the acetylene gas. You will just end up with this. And you know that double bond can be reduced, controlled reductions can be done by Lindblad catalyst. Okay, if you do the normal hydrogenation, you will end up with the single bond. But if you do the Lindblad reduction, that is hydrogenation, that is a PSO4 you have to use as a auxiliary catalyst, which poison the palladium for the controlled reactions, and which will give the double bond, and that is what you target. Okay, so this target, this is what the target. Okay, now if you want to have alternative way, which is already we have discussed here, alternative way, another way, that is directly using the vinyl magnesium bromide, and you will get this. So this is what, how you can tackle the synthesis of this particular tertiary alcohol. Now look at this big molecules. Looks ether, cyclic ether. But you have to think that this is something like having a specific geometry, that is cis alkene. Okay, and this is a protected form of, you can say, the ketone, or protected form of the diol. Okay, so this is sort of acetal cyclic ether. So if I disconnect over here and here, this is nothing but the acetone, and this will be the diol. And this diol having a primary alcohol, and this is unique to disconnect over here, having a symmetry. So this is the part of acetylene again. If you do the FGR, so this is acetylene and this is a formaldehyde. So 2 moles of formaldehyde when reacts with acetylene in presence of basic medium particle, because the acetylene will be active or reactive, particularly in proper words, in presence of base, because of the active proton. Okay, these protons are active. So these protons react with the base, becomes a nucleophilic, and then the formaldehyde will react and you will get the primary alcohol. And this primary alcohol will be reduced with the Lindblad catalyst again, and you will have a cis geometry, because Lindblad will give the stereo selective reduction. That is, we call it the stereo selective, because it is starting material oriented or product oriented, because you are using here triple bond, you reduce it and you are getting exclusively a cis product, not a trans. That's why it is a stereo selective. And then you protect it. This is just the protection of acetone, and you will get the cyclic acetal type of compound. Okay. Move on to the next. Now look at this molecule. This is a bit interesting one. Now here, many times in the net set examination, these examples were asked many times. When I was a student 20 years back, I remember this problem was there where we used to give the physical writing exam, like we had to write the paper. Now it is MCQ pattern, but very much I remember this particular problem. Now look at here. This is a double bonded compound, that is cyclohexene. Now, whenever you come across with the double bond, you think some point, okay, it may be the Wittig reaction, but in cyclic compound, it is not possible to have the Wittig sort of chemistry. Okay, so if you go for the Wittig type of chemistry, it will waste your lots of energy, because if you disconnect over here, and then it will be the carbonyl, and then you will have some sort of alkyl halide with this, and it is a complicated matter. So need not to think that way, but you just think in the fashion of conversion of the double bond. Normally, whenever you come across with the double bonded compound, you have to think that double bond can be flexible, that it may be the part of dehydration of alcohol, the double bond means. So why don't we go for the hydrations for retrosynthesis? So what we are going to do here, for this double bond, we did the FGI. What FGI means, that we are going to do the hydration, that is a dehydration. You have to write opposite way, that is a dehydration. If you do the dehydration of this, you will end up with this alkene. Now, this addition of particularly water molecules, if we do OH addition over here, all right, and H over here, you will have these molecules. Okay, but if you add OH molecule in other way around, so this you will end up with this, and which will not helpful in the synthesis. Okay, but this particular alcohol, now tertiary alcohol, will be very useful. Whenever we come across with a tertiary alcohol, our job is very easy, because we know that tertiary alcohols, or maybe the secondary alcohol, or it may be the primary alcohol, can be easily targeted because of the Grignard reagents and the carbonyl group. So if I disconnect over here, this will give you the phenyl magnesium bromide like this, and this will be the cyclohexanone. That is a cyclic ketone. Now, this cyclohexanone, when react with your PHMGPR, you will get the alcohol, this. So this is this, or this is this here. This cyclohexanone, when reacts with PHMGPR, you will get this alcohol. On dehydration, use the H2SO4, you will get the target molecules. Okay, so this is how we have done the synthesis. Now, this is all about the alcohol. Now, another important functional group is the carbonyl group, and that includes aldehydes, that includes carbonyl as ketone, as well as ester, amide, and so on. Now, let's target with the ketone first. Now, this is your ketone. Now, ketone, particularly aldehyde, they are again flexible in terms of the alcohol transformations. We know that primary alcohols can be easily converted to the aldehyde by control oxidations. And your secondary alcohol can be converted to the ketone, or ketone can be converted to the secondary alcohol. So these two things are very much flexible. While doing the retro analysis, you can play with that convergence, or you can play with that transformations. Now suppose our target is a ketone. Now this ketone is not so easy to track in the synthesis. So what we are going to do, we are convert it through FGI, that is we call it as a functional group interconversion. And you end up with a secondary alcohol. Now, just now we have discussed the secondary alcohol, how to tackle in the retro analysis. So we disconnect over here, or we can disconnect over here also. That depends on you, whether you got this GR available or this GR is available. Suppose we are disconnect from this end, you will have here this particular GR and this propanol. Now, if this is not available, you can go one step ahead to synthesize this also. Okay, but in simple language, if this available, then we will simply proceed with this, and you will end up with the target molecules. Okay, Suppose we thought, no, we have this alkyl magnesium bromide available in the laboratory. So we can think about this way. We disconnect over here. We have here alkyl ethyl magnesium bromide, and this particular ketone we have. So then we can think about this type of synthesis also. So there is a another way to have this synthesis. Another example based on the ketone. So this is the already I think we have discussed yesterday, but still I will show you one applications of this. That suppose we have here this big molecule to be synthesized. Okay, yesterday we have tackled this one. If you disconnect over here, you will have here acetyl, and this is your anisole, and this simple acylation of anisole will end up with this acetophenol derivative. Now, this reaction is related to these molecules. How? Now, if you are targeting these molecules, you will disconnect over here, or you will disconnect over here, or it may be here possible. Okay. Now, if I disconnect over here, particularly this A root, okay, what I will get? I will get acyl group. Okay, this acylation, how I will do it here in a similar fashion. But if I do the disconnection over here, let me just off. There are two ways. If I do the disconnection over here, it is impossible to have acylation across the alkyl group. So I don't think about this. Okay, I don't think about this then. Suppose if I disconnect over here, then I will have alkyl group over here. So alkylation of the aromatic ring is bit tough. Instead, acylation. So what we'll prefer? The A route, which gives the acyl group, which will be preferred over the alkyl. So this can easily work out, and then your synthesis will be very comfortable. Okay. Now, some point, the residue selectivity is the really a major issue in the synthesis, because in case of ketone particularly, suppose we have acetone over here. Now this is your acetone. We'll have both the sides, this side as well as this alpha side is same in terms of the electronegativity or acidity particularly. Now when the base is treated with this, the base can abstract the proton from here and base can abstract proton from here. So if I do the alkylations, so this nucleophile attack with this halide and you will have addition. But there is no guarantee that the alkyl group will be added across one position only. There may be the possibility to have the addition of this alkyl group to this side. So selectivity in terms of the regio. Regio word means a place, where to react, where to go. रेजियो सेलेक्टिविटी इन अ सिंपल लैंग्वेज, हमें अपने घर में ही जाना है, दूसरे के घर में जाना नहीं है. दैट इज वी आर फिक्स, आवर रूट्स आर फिक्स. हमें हमारे गांव को जाना है तो हमारा रूट ये ही रहेगा फिक्स. दैट इज व्हाट रेजियो सेलेक्टिविटी. दैट मींस पोजीशन ऑफ दैट पर्टिकुलर रिएजेंट विल बी फिक्स कि इसको यहाँ पे ही जाना है. जैसे कि मुझे इफ आई वांटेड टू टारगेट दिस वन, I know that if I disconnect over here, this fragment should go to this position only. But if both the doors are open, like in the house, if we having a multiple way to enter, then anybody can enter from anywhere. Okay, so there should be a one particular proper door, and that proper door can be given by applying the some selectivity concept, and that selectivity concept will be possible by using some uh, uh, we have to use some reagent instead of using that particular target molecule. So you have to take the help of auxiliary type of starting material, which is not actual starting material. So it will helpful, but in the last stage, that particular part will disintegrate from that starting material and you will get the target molecule. So how to understand this particular concept now? I will take the example first. Now, what is this example? My target is to synthesize this molecule. So what I did, I disconnect over here as I shown here. Then what I will get here, I will get here two fragments. What two fragments? This acetone one, and another one is your something benzyl bromide type of compound here. So if I do the reactions, whether I will get this one or I will get this one. So these are the two possibilities. If instead, if I use instead this acetone as a ethyl acetate acid as a starting material, where the active methylene is very much reactive as compared to the alpha hydrogen from this side. यहाँ से ये वाला जो methyl group है, it's tremendously acidic. Why? Because of the ester as well as ketone. It is trapped in between the two electron withdrawing groups. So the activity is very fast. So the mild base can work the job of deprotonation, and the reaction works very fantastic. So when we treat this with uh, a mild base, any base, you can just use a potassium carbonate as well instead of ethoxide. Ethoxide is much more basic. So if you use a potassium carbonate type of base also, this will deprotonate, and this phenyl magnesium this benzyl bromide will be added, and you will get the alkyl electrons across the one position only, not to these positions, because we have used a mild base. Now we don't want this ester group because there is no need as such in the target molecules which we got target. Here there is no any ester. So what we can do, ester can be disintegrate or decarboxylate from the molecules by the simple process of hydrolysis. Ester hydrolysis, you know that you have to use alkali and heat it strongly, that first the ester will be hydrolyzed and then the CO2 will go off, and the process of purification will be very easy because CO2 will go off and ethanol will be the solvent. So this way you can do the decarboxylations and you can get the access to the target molecules very selectively. That is what we call as a regioselectivity. Okay, so this is the way, just I have mentioned one slide, how to decarboxylate. This is your target now. Sorry, this is your product form. So hydrolysis and then disintegration, CO2 will go out and you will get this particular target molecule. So this is what the way to get the access to the your targeted molecules. Now I have another example, which is again the very systematic use of some auxiliary type of compound to get the access to these molecules. Now suppose we have these target molecules. Okay. Now these target molecules have something like chain of carboxylic acid over here, allylic chain with carboxylic. Now suppose if I disconnect over here, I will get here this will be a sort of, suppose if I consider this as your minus, this will be a plus. Okay. Now to have the positive charge across this like acetic acid, suppose CH3 COOH. Okay. Now to use an acetic acid or maybe the your methyl or ethyl ester acetate particularly, and then I will do the Grignard reagent reactions. I will end up with this product. But is it so easy that acetic acid or maybe the ethyl ester is so reactive for such types of alkylation? It is not. So this particular methyl group is not so reactive. So what we can use as an auxiliary reagent instead of using this acid derivative, we're going to use a malonic ester. So this is what we are going to use, a malonic ester. So if we end up with, so we can change here the charges. Actually, this should be your minus and this should be a plus. Okay, so this particular part, this is a synthon. This synthon is nothing but taken as a ethyl malonate, which is a bit stable as well as most reactive, and this will be going to consider as a, this will be considered as a your sort of you can say here positive charge over here. Okay, so if it is a your negative charge, so this will be the positive charge, and this positive charge can be taken by these halide positions. Okay, and now this further can be synthesized by doing some FGI. It will be converted into alcohol, and then primary alcohol, you know that it's a product of reduction of ester. So we did further FGI. We got here cyclic compound. Now, whenever we end up with this cyclic, that is cyclohexene type of compound or derivative of cyclohexene type of compound, you have to think about the some sort of the known chemistry, that is a diol reaction. So if we disconnect over here, this will end up with the diene, and this will be the dienophile. Okay, so this dienophile and this is your diene. So this will give you the diol product, which when react you will get here this. Okay, on the reductions, this will give the primary alcohol followed by a PBr3 treatment. You will get the halide, and then halide undergo the alkylations with this particular malonate, and you will end up with the target molecules. Now, we don't want both the carboxylate group here. So we do the hydrolysis followed by decarboxylations. You will end up with the target molecule. So this is the way how to use the that synthetic equivalent molecules, which are point not exactly same to that, but which do the exactly the same job of what we are required in the molecule as a fragment. Okay, so more to the next. Okay, this is the another example. When we do the disconnections, again you have to follow some sort of orientations that already we have discussed yesterday, but have just one example. Suppose we have here this molecule, huge molecules. We are disconnected over here. If I disconnect over here, A path, you will get this acyl group, that is a benzoyl group, and this anisole type of derivative. And then if I disconnect by B, then you will have nitrobenzene here and this benzoyl type of group here. Now we know that this nitro group is meta-directing. So when this react with this, the reactivity will be on meta position instead on para. Whereas this particular nitro derivative of acyl group will definitely will react with the ortho position because the para is blocked, and because of this OH, this will go to this ortho position, and this will be very easy to tackle the synthesis. So some point you will have more than one options, but you have to think about the orientation as well. Okay, more to the other example of amide functional group now. Now this is amide. Okay, you know that amide can be easily synthesized by the process of amide, uh, that is amine, and when acid chloride or acid will react together, there is a amide bond formation. This simple synthesis we all know. Now in the same way we are going to move ahead, that this is amide bond, we are going to disconnect. In the disconnection arrow you have to write carbon nitrogen disconnection, carbon nitrogen of amide bond particular. So if we disconnect over here, we'll get here piperidine, and we will get here acid derivative, the carboxylic acid. Now, if you want to synthesize this acid, which will not be available, then you can go ahead with the synthesis of this, but the piperidine will be definitely available. So if you want to synthesize this carboxylic acid, you can do it, do the disconnection over here. If I disconnect over here, this will be the, no doubt, this will be the negative charge and this will be positive charge. That means this COH will be the part of carbon dioxide, and this will be the GR. And if this further are not possible, then you can synthesize again, go one step back, convert this into the halide followed by the alcohol. And alcohol can be, you know that now how to synthesize. Disconnect over here, you will have here this part of carboxyl aldehyde, and this part will be the Grignard reagent. And then when this react, particularly this one, okay, will be synthesized in C2 and react with the uh, propanol. This propanol over here return. You will get this alcohol treated with PBr3 and followed by Mg, and treated with the CO2, you will end up with this carboxylic acid, which on acylation, that is what, sorry, which on chlorinations, with the help of thionyl chloride, you will get the acetyl chloride of this, and then this acetyl chloride react with the piperidine, you will get the target molecule. So this is how the amide is also very useful to have a convergent type of synthesis. Now look, this is a big conversion because this piperidine is one fragment of this molecule and this carboxylic will be the another. So when these two fragments join together, it looks similarly to that of convergent type of synthesis. Another example where you will come across with only the alkene. Now there is no any functional group. And whenever you come across with the just a double bond, already we have mentioned in the example that double bond can be as a at the cost of the dehydration. So we can do the hydration for the easy way. So if you have a double bond, you can do the you can convert that into the alcohol by placing the hydroxyl group over here or over here. So you will have both the possibility, and accordingly, according to the availability of the starting material, you can choose which you want. Suppose we have selected A, added OH over here, then we will do the disconnections over here or here, and accordingly we can do the synthesis. Okay, so this type of synthesis already we are discussed. There is an alternative to have this particular double bond. That alternative method is Wittig reactions. Suppose we want this quick access to this, and we don't have the assembly where the Grignard reagents can be used. So then you can use an easy way another, that is the Wittig reaction. If you disconnect over here, this is nothing but the ketone, that is acetone, and this nothing but the ylide, that is a phosphorus ylide, which can be easily synthesized by using the triphenyl phosphine and this halide. When they react together in presence of strong alkali, they will give the Wittig salt, and this Wittig salt again react with the ketone in a basic conditions, will get the olefin. That is what the olefinations. Okay, so this is what how quickly you will get the access to the double bond as well. All right. Now, again, the another example of sort of chemistry, that is a double bond. This double bond can be easily assessed by Wittig chemistry. How this Wittig chemistry can be worked? Suppose I had disconnect over here. This is the part of your ketone, this remaining, sorry, aldehyde, and this remaining is your Wittig salt. Now, this Wittig salt will be the part of your halide. Suppose if this halide is not possible, then you can easily go for the synthesis of this. Other way around, you can take this side of Wittig and this side will be the aldehyde. So both way it is possible. So this is aldehyde and this is Wittig now. And this Wittig can be synthesized from this. So this particular synthesis of cyclic ketone, cyclic aldehyde, it is easy because there is a double bond in cyclic 6-member ring. So the Diels-Alder concept can be possible over here. So if you disconnect over there, you can have easily dine and dinophile. So this is your dinophile from this, okay, and this is your di. So you can easily have access to this. So over these two methods, this one or this one, so B will be preferable over the A because this will give the very high yielding steps of the reaction. That is what we call as a Diels-Alder reaction, which is the part of green chemistry because having the 100% yield. Okay, so we have in the process of retrosynthesis, it was there that you have to select the high yielding steps. So we have selected this one, Diels-Alder steps. So you got here this ketone and treat it with the phenyl magnesium, sorry, this Wittig reagent, and you will end up with the target molecule. So it is very simple. So this Wittig reagent and this aldehyde react, you will get target molecules. Look at the another example where there is no any functional group as such. If suppose we don't have any functionality in the molecule, then what to do? As I told you yesterday, if there is no any functional group, if you are having only alkane, then you can add the double bond, and then the double bond can be added in a way that if there is any phenyl ring, it should be close to that phenyl ring because the addition of phenyl ring, it will be easy and preferable one. Okay, so if I do place the double bond over here, I can disconnect over here, I can use here Wittig chemistry, or I can go one more steps ahead that I can add a water molecule over here, okay, over here like this, and I can disconnect this particular or this one, and I will get here benzaldehyde over here, this, and this will be your nothing but the uh, your Grignard reagent and treat it with, you will get the uh, alcohol, do the dehydration, you will get back on reductions, your target molecule. So multiple way you can tackle this sort of chemistry. So this above chemistry is both way, you can use Grignard reagents as well as Wittig salt. Okay. Now, another hydrocarbons here. Looks very simple. Looks very simple to synthesize, but how to tackle? Now look at here. So this is your cyclohexyl benzene. Now this cyclohexyl benzene, how to synthesize? It looks very simple, but it's a selective in terms of reductions. Suppose we have here diphenyl compound, and suppose you are targeted, okay, I will select one ring to be hydrogenated. How it is possible? You cannot control the reactions that the one ring will get reduced. It is impossible that way. Both the rings, because these reductions, if you do the hydrogenations, it will be on high pressure. Under the high pressure, there is no any assembly to control the reactions at one ring. So it is impossible to go with the hydrogenation process. So how to do the synthesis of such types of hydrocarbon then? Then we have to use the addition and removal of the functional group strategy. What is that addition of functional group? Take this as target molecules. I have added the functional group, this double bond. Now this double bond is added over here. Now then again I have added a functional group called as hydroxyl group, that is called as hydrolysis. Addition of hydration, we can say, not hydrolysis, hydration. So add water molecules and we end up with the tertiary alcohol. And once we end up with the tertiary alcohol, it is very easy way to do the synthesis. Just do the cleavage over here. You will get the phenyl magnesium bromide, and this is your cyclohexanone. So this is cheaply available material. To treat this together, you will get here alcohol. To the dehydration, you will get the alkene. To the reduction with the hydrogenations, you will get here simple reduction of this double bond. Simple balloon pressure is enough to reduce this double bond to this cyclohexane derivative. So this is how to tackle this particular carbohydrate to be synthesized. Now look at here, the another one group. We are talking about the one group carbon-carbon disconnections, but here now we are going to use some sort of via chemistry, that is alkene via acetylene, because we are going to think about the selectivity in terms of the stereochemistry. Now suppose we have a target, these molecules, and where this double bond in this molecule is having some specific stereochemistry, and the stereochemistry is cis geometry of the alkene. Now the cis geometry of the alkene, if you have, then you should logically think about the reaction called as Lindblad reduction. So that means in the molecules you have to incorporate it somehow acetylene triple bond compound, and then you have to reduce it to the double bond by using the Lindblad condition. Suppose if you have this one as a trans geometry, suppose I would say, then you have to use the another reagents you have available, that is we call it the Birch reductions, which gives you the acetylene, that is a triple bond compound to the trans geometry olefin. So that way you have to logically think now. This compound not as such given, okay, this is the just simple your ketone having a double bond compound, but there is a specificity, specific stereochemistry mentioned. So you have to be in a logical way to synthesize that proper geometry in the molecules. So how to target this molecule now? Suppose we have here this compound. So first FGI you have to do that double bond, you have to convert into the triple bond, and then you have to alkylate this acetylene. That acetylene can be easily methylated by using the methyl iodide, and this methyl iodide will react with acetylene anion, and it will be giving this one. But how to get this assays? So you can easily get this assays particularly by doing further chemistry over here, that you can disconnect over here, okay, and you will have here a sort of derivative of the acetylene, okay, that is a halide with acetylene derivative. So this particular acetone can be selected as a active methylene compound, that is a ethyl acetate, ethyl acetoacetate. And as we have seen the chemistry, how it easily works with any electrophile. So this is the electrophile and this is a good nucleophile. They react together. So in this chemistry, you will have this particular structure. We got up to this. We don't want this ester, so we do the hydrolysis in the further steps. Then we do protect this ketone, okay, and then we have treated with amide, because we have to protect here amide, sorry, carbonyl group, because we are going to treat it with amide. Otherwise, it will interfere in the reactions. And then this alkylation is possible. So we did the alkylations. And this hydrolysis of this will give the carbonyl group. And in the last stage, we do the reduction. But that reduction is what? In the presence of barium sulfate, that is a poison for the palladium, to control the reactivity of metal. And you will end up with the target molecule, which is your cis geometry of the olefin. So this is how to get the access to the stereochemistry. Now there is another one group carbon-carbon disconnections, including the functional group called as nitro and nitrile, which are another very important functional group in the synthesis point of view, because it generate the assays for the reactions, increasing the or decreasing the pool of electron, particularly because of the electron withdrawing nature. Or it can be flexible to convert the nitro to amine, or nitrile to ascending carbon of the amine, that is one carbon extra. So that way, this nitro and nitrile having the huge application in the organic synthesis. So let's have some of the examples. Suppose we have target this amine, and how to synthesize this amine. So what we will do, we'll do convert this amine particularly into the nitrile. So this particularly CH2NH2 will be converted as this nitrile, because if we do the reduction of this, you will get one carbon extra, that one carbon extra over here. Okay, now here there are two carbon, now here there are two carbon, 1 and 2 and NH2. So here we have one carbon from the carbon of the CH2 and one carbon from the functional group of the nitrile group. But when we reduce this triple bond, carbon-carbon triple bond, the nitrogen will give the NH2 here, this one, and this carbon will give the CH2. So this way it is very easy to have one carbon extra, that is ascending of the carbon. Normally in the interviews, the panelists normally ask the questions, can you just quote any example where you will ascend the carbon in the reaction? So this is the cyanohydrin type of chemistry is the best example, or nucleophilic substitution with the cyanide. That is also the way to answer. Now, this cyanide can be incorporated by simple nucleophilic substitution reaction with the halide. So this halide can be implanted very easily by doing the chloromethylation, formaldehyde and HCl. If you treat together on aromatic ring, you will get here that is chloromethylation. So how to start the synthesis? That synthesis will be very simple. That you will have this catechol derivative, which is protected, and then there will be the chloromethylation. You will get this. Then this will be treated with the sodium cyanide. You will get this nitrile group over here. Do the reduction, you will get this compound. Now the same compound can be tackled by another way, that you can use the nitro compound instead of NH2 as a functional group. That is FGI. Suppose I have changed the functionality from NH2 to NO2. I can do this nitration, and I can have the back this NH2 group by simple reduction with maybe the hydrogenation, or you can use the lithium aluminum hydride, or another simple reagent is like metal in presence of acid like SnHCl, tin, and HCl. So lots of reagents are available to reduce the nitro groups to the amino groups. Now suppose we end up with a nitro, then what we will have, this nitro can be further converted into the another FGI, that is we call as a double bond, that is alpha beta unsaturated nitro compound. Now this alpha beta unsaturated compound can be easily synthesized by sort of condensation reaction. Suppose we cleave here, so this will be the benzaldehyde type of derivative, and this is your nitromethane. When the nitromethane in presence of strong alkali react with the aldehyde, this will give you the Novengel type of condensations, and that gives you the alpha beta nitro compound. And this alpha beta nitro compound can be reduced by maybe the hydrogenation. If you do the hydrogenation in one stroke, you can have the reduction of the double bond as well as the nitro compound, and you will end up with this compound. So this way how simple to tackle this sort of molecules by both the way by using the nitrile as well as the nitro. Let's see some of the same synthesis over here. Okay, already I think I have discussed with you that. Another example to tackle some sort of similar type of chemistry. So this is a target molecules. Convert this into the nitro. This nitro now, again FGI, you can add a double bond in the 6-member ring. Now, if you have a 6-member ring like this, you can play with this ring by adding a double bond and do the Diels-Alder type of chemistry. Suppose if I add a double bond, I can have a Diels-Alder chemistry. I will disconnect over here. I will have a diene and dienophile. Now, the stereochemistry of this particular substituent, that is phenyl and nitro, is a trans. So when we disconnect over here, the dienophile will be having a trans geometry that you have to look into. So this trans geometry of this dienophile, you have to selectively synthesize. It can be possible by, if you disconnect over here, this will be the benzaldehyde and this is nitromethane. When they react together, obviously you will have both the isomers possible here because it will be diastereoselective reaction. You can resolve that and then you can select the trans geometry one and you can proceed with the reaction. So this benzaldehyde, when reacts with the nitromethane, you will get this alpha beta unsaturated nitro compound. On Diels-Alder reactions, you will end up with this particular cyclohexene, and then on hydrogenations, you will end up with the your target molecules. So this is so simple chemistry over here. All right, now I think we will stop over here. So rest of the topic related to 1, 2, 1, 3, 1, 3, 1, 4, 1, 5, 1, 6 difunctional compound and their disconnections with the very interesting examples we are going to discuss in the next session, which will be starting 3 o'clock exactly. If you have any doubts related to this topic, you can post it in the WhatsApp group so I can answer it. Let me just check, is there any questions asked in the chat box? Okay, somebody has asked one question. During electrophilic substitution, anisole is orthopara directing because OMe group having, okay, that's true. That is correct. During acylation of anisole, why acyl group is attached to para and why not attached to the meta position? Anisole is if you know, anisole having a OH group. OH group is what? Sorry, OCH3 group, which is a electron donating group. Okay, and because of that effect, it is showing the orthopara directions. Okay, then slide 19, disconnection B can be with the mixture of product. Okay, isn't it? Okay, let me just have a look. 19, slide 19. Let me just have a look. Okay, 19. What is question? Okay, slide 19, disconnection B. Okay, gives mixture of product. Now listen, this B route normally we don't go for because it is not so easy to tackle to get these molecules. So that's why if you do the particularly dehydrations, you will get the double bond to this side and to this side, and which is not fitting to this geometry of this molecule, which is our target. That's true. Slide 17. What is the role of HBr? Okay, just let me just go to the 17th slide. Slide 17. Okay, what is the role of HBr in the last step? HB. Okay, look here. Some sort of some extension was there, but in fact I have deleted that. So ignore these sort of things because we have ended to this target molecules. Okay, so just ignore this because I have edited that slide. So some point may be missing out. Sir, explain the catalytic poisoning in case of H2. Okay, so this is a very well-known phenomena. Lindblad catalyst, you know the Lindblad catalyst, which is uh, use of palladium particularly, the very active metal, which is having a huge surface. Now, when we are using this particular metal for the hydrogenation purpose, so it's regenerate its activity if you use only palladium in the hydrogenation process, because it's a metal. But when we use a sulfur-based compound like barium sulfate, what will happen? The activity of palladium will get reduced. Like sulfurs are the particular sulfur-based compounds are the most dangerous in case of poisoning of the heavy metals particularly. That's why we have used here beryllium sulfate. We use here suppose like some sort of sulfur-based any pure compound, the palladium would not work at all. So it poisons, it reduces the reactivity of that particular metal. That's why we have used here. Okay. So anyway, I have responded to the all questions. Hopefully, you will understand. And definitely in the last sessions, you must have more questions, and that all questions will be welcome. And in future also, if you have any doubt related to the related to the retrosynthesis or any chemistry so far, I'm not just restrict you being a student's uh, platform here. So I can welcome all the queries related to the chemistry on the WhatsApp group only. Thank you very much indeed. And we will start exactly 3 o'clock.